Hey everybody, welcome to Algo Expert. In this video, we're going to be covering the question of the two-number sum. This question basically gives you an array of distinct integer values, meaning that no number in this array is repeated. And it also gives you a separate integer value that represents a target sum. And what you have to do is write a function that's going to find whether or not there's a pair of numbers in this array that you're given that sums up to the target sum. So in this example, we've got the numbers 3, 5, -4, 8, 11, 1, -1, 6, and we've got the target sum 10. We want to find if there's a pair of two numbers here that sum up to 10, and there is. We can have the numbers 11 and -1, which do indeed sum up to 10. 11 plus -1 is equal to 10. So I really like this question because it's the first of a few of its type, meaning on algoexpert.io, you'll actually find two other questions in the array section or category. One of them is called three-number sum. The other one is called four-number sum. And they're very similar to this question, except they ask you to find a triplet that sums up to a target sum, or a quadruplet, four numbers. But this question is the easiest of the three. It only involves two numbers. That being said, it's important to understand this one because it'll teach you a lot and it'll prepare you for these tougher questions. So how do we do this? How do we go about implementing an algorithm that'll, traverse this array and somehow find the solution? The first thought that you might have is to kind of use two for loops and traverse the array twice to find the sum. And that would work, right? You could traverse the array once, go through each of the numbers individually, and then at each number, traverse through the rest of the array and try to find the sum. In other words, you could start at 3 and traverse all the other numbers here and see if adding any of these numbers to 3 yields 10. Then you move on to 5 and you traverse all the other numbers and see if adding any of them to 5 gives 10, and so on and so forth, right? But the thing is, that's not very optimal from a time point of view, right? That's going to take O then squared time because you're going to be doing two for loops. So perhaps a better way of solving this here is to use a hash table. Now that's going to cost extra space, but it might make our algorithm faster. So what do I mean by using a hash table? Well, basically, we can traverse our array here and store every number that we see in a hash table, which is going to allow us to then access these numbers in constant time through that hash table. So I'll write in green here. Let's say we have a hash table at the top, which you can represent as, a Python dictionary or a JavaScript object, whatever you want in your language of choice. But so now that we have this hash table of numbers, we're going to traverse our array, and at each of the numbers that we traverse, right, at each of the numbers that we stop at, we're going to check if the number needed to sum up to the target value, which is 10, is stored in this hash table. So in other words, we've got our target sum, right? We've got target sum is equal to 10. And whenever we're traversing the array, we've got a current num, let's call it current num, which is equal to x. X is whatever number we're at as we traverse the array. And so we want to find y, the number y, such that x plus y is equal to 10. Or in other words, we can isolate y to be y is equal to 10 minus x. So basically, as we traverse the array, we have the value 10, which is our target sum. We have the value x, which is whatever number we're currently at. And all we need to do is apply this formula or solve this equation to find y. And then we say if y is in our hash table, and we can do that in constant time, accessing y in the hash table. If it is in the hash table, then we just return x and y. Otherwise, we keep traversing the array, and we just make sure to store x in the hash table. So here, let's see how this is going to look. We start at the number 3, and we say, okay, y is going to be equal to, we're going to write it in, let's write it in white, y is going to be equal to 10 minus 3. In other words, y is going to be equal to 7. Is 7 in our hash table? No, it's not. So we haven't found the two-number sum so far. But what we can do now is we can store 3 in our hash table. We can store 3 to be true, or whatever value you want to store it as. True here just kind of indicates that, yes, 3 is present in our array. So now we move on to 5. And we say, okay, if we have the number 5, let's solve for y. So here we're going to say 10 minus 5 is equal to 5. And is 5 in our hash table? No, it's not. So we skip this. We haven't found our two-number sum. And all we're going to do is store the number 5 here in our hash table as true. Let's add a couple of commas here. Then we move on to the number minus 4. And we solve for y. So we say, is 10 minus negative 4 equal? So 10 minus negative 4 is going to be equal to 14. Is 14 in our hash table? No, it's not. So we just store negative 4 to be true in our hash table. Then we get to this 8. We solve for y. So 10 minus 8 is going to be equal to 2. Is 2 in our hash table? No, it's not. We only have 3, 5, and negative 4. So we can skip this, and we can just store 8 as true. And you kind of get the idea now, right? So the rest of this should go pretty fast. We go to 11, solve for y. 10 minus 11 is going to be equal to negative 1. So that's not going to be, is negative 1 in our hash table? No, it's not. At least not yet. So we just store 11. Then we move on to this 1. We do 10 minus 1. That's going to be equal to 9. 9 is not in our hash table, so we just store 1. And now we get to the number that we care about. We get to negative 1. So we can calculate 10 minus negative 1. That's going to be equal to 11. And now if we check for the number 11 in our hash table, well, we'll notice that we have it here, right? And so because 11 is in our hash table, that means that we know we've traversed it in our array. We've traversed through it. So now we can just return 11 and negative 1, and we're done. So now we can just say, return 11 and negative 1, and we're done. We've found our answer. So how are we doing in terms of space-time complexity analysis? Well, let's write it at the top left here. The time complexity here is just going to be O of n time, where n represents the length of our input array. Why is it just O of n time? Well, we're traversing our array only once. And at each number, all we're doing is calculating y, right? Solving for y. That's just a constant time operation. We're just doing a calculation. We have the target sum. We have the number x here, which is whatever the current number we're at. And then we're just accessing values in a hash table, which is going to run in constant time. So in total, time complexity is O of n. Now, the space complexity is also going to be O of n, because we are adding values to a hash table. And so here we kind of saw that we went all the way to this negative 1, which was kind of, the before last number in our array, so we did store a bunch of values which kind of neared n values in our hash table. So the space complexity is going to be O of n. If we had done this using just 2 for loops without a hash table, then we probably wouldn't have used additional space. We would have gotten constant space, but we would have gotten O of n squared time because of the double for loops and the sort of double iteration through the array. Anyway, that's it for the conceptual overview of this algorithm. Let's see what it looks like in code. So before we dive into the code walkthrough, I have to apologize because I just realized that I totally forgot while I was filming the video to mention a third way that we can solve this problem that is definitely worth mentioning and worth covering, so I'm going to do it now. It doesn't use a hash table, and it's more optimal than the first solution, using double for loops. So let's dive into it. Basically, we had this array of numbers, right? And when we were given the array of numbers, we weren't told anything about it. In other words, the array wasn't necessarily sorted. But we can solve this problem more optimally without using a hash table by first sorting the array, more optimally than the solution with 2 for loops. So if we sort the array, here I've got the sorted array. We know that, good sorting algorithms like quicksort or merge sort or heap sort will take O of n log n time. So we can have a time complexity of O of n log n. And then we can actually find the answer, which is going to be 11 and -1 here, in O of n time. And because we can find it in O of n time, we have a total space or a total time complexity of O of n log n from the sorting at the beginning. And we don't use any additional space, so O of 1 space. So let's dive into actually how this works. Basically, what we can do is, once we've sorted this array, and by the way, the same logic is applied in another question on the website, the one called 3-number sum. So if you're interested, definitely go check that one out as well. But so what we can do is we can put a left pointer, initialize it to be under the first number in the array. So we've got a big L here representing a left pointer, and we can put a right pointer under the very last number in the array, in this case 11. And so what we can do is we can sum up the two numbers that L and R point to. So we have -4 plus 11. And once we have this sum, we can compare the sum to our number. So this sum is going to be 7. And so we can compare 7 to 10. Now, is 7 equal to 10? No, it's not. So this is not a valid sum, right? -4 and 11 are not a valid sum. But what we can say now is, we know that 7 is less than 10, right? And if 7 is less than 10, and all of our numbers here are in sorted order, then what would happen if we were to move the right pointer? Well, if we were to move the right pointer to the left, right here, to this 8, we know that this 8 is less than 11 because the array is sorted. And because 8 is less than 11, then our new sum here is going to be even smaller than 7, which is already smaller than 10. So instead of moving the right pointer to the left, we know that we should move the left pointer to the right, because we want to try to have a greater sum. And so if we move the left pointer to the right, then we get this -1. And so we can update our sum to be -1 plus 11 equals to 10. And now we have our actual answer, because 10 is equal to 10. But now here, let's actually let's try to come up with a different example to make this more interesting. Let's assume that our answer had been 16. Okay, so 11 plus 5, or rather, no, not 11 plus 5. Let's assume that it had been 13. 8 plus 5. Okay, so if we were looking for the number 13, and the answer was 8 plus 5. 8 plus 5. Then what we could do is we would have we would have here the sum 10, and 10 would be smaller than 13. So we'd once again move the left pointer to the right by 1, because we know that moving the right pointer to the left would give us a smaller sum, which would be smaller than 10, which would be smaller than 13 for sure. So we move the left pointer. Now we've got 1 plus 11 is going to be equal to 12. So we compare 12 to our target, which is 13. 12 is less than 13. So once again, we have a sum that is too small. So we can move the left pointer to the right. Now we have 3. So we sum 3 and 11. And we can erase this. 3 plus 11 is going to be equal to 14. And now 14 is greater than 13. So our sum is bigger, right? Our sum is too big. So what can we do? We know that if we move the left pointer to the right, we're going to have a number that's bigger. We're going to have a greater sum, so we don't want that. We know that moving the left pointer to the left doesn't do anything because we've already tried all these numbers. So what we do is we move this time around the right pointer to the left. And so now we've got 3 and 8. 8 is smaller than 11, so we're going to have a smaller sum. So we can update this 11 here to be 8, and 3 plus 8 is going to be equal to 11. So is 11 equal to 13? No, it's not. It's less than 13. So again, this time around, we're going to want to move the left pointer to the right. Just to make sure that we're on the same page, the reason we don't want to move the right pointer to the right, which would be a bigger number, is because we've already calculated sums using this number 11, and we eliminated all of them. So we want to move the left pointer. So we move the left pointer to the right. Now we've got 5 plus 8. So 5 plus 8. And 5 plus 8 is going to give us 13, the number that we want. And that is our answer. And so the reason this is a really nice way to solve this problem is because we don't use additional space. You know, we just have a left pointer and a right pointer, but that's that is constant space. We don't use an extra hash table or anything. And in terms of time, we actually run in O of n log n, because that's how long a great sorting algorithm like quicksort would run. And the actual algorithm that we just described here with the left and right pointers runs in O of n time, because at the most, we're going to be moving the left pointer to the right every time, the right pointer to the left every time, and eventually they get equal to each other. And in total, all we've done is go through all the numbers, once or twice. And so that converges to O of n time. Therefore, we can write the time to be O of n log n, and the space can be written as O of 1, which is constant space. So this is a really cool way to solve this algorithm. Once again, I apologize for having forgotten about it. It's definitely covered in the 3-number sum question, so definitely check it out if you want to re-see how it works, and in the context of that question, which is a bit more complicated. And now let's actually dive into the code walkthrough of all these solutions. All right, so we've got our 2-number sum function defined. It takes in an array of distinct integers and an integer value representing the target sum. And so we're first going to type out the solution using the 2 for loops, which is going to run in O of n squared time, where n represents the length of the array. For that solution, all we have to do is literally implement 2 for loops. So we'll say for I in range len of array -1. We want to go all the way to the before last value in the array. And then we can say current num, or rather first num. We can kind of declare our first num variable is going to be equal to array of I. And then we can say for j in range I plus 1 len of array. Here we can, we're iterating through all the rest of the numbers in the array. We can say second num is going to be equal to array of j. And here it's important that j goes all the way to the end of the array, right? And then we say if first num plus second num equals target sum, then just return an array of first num and second num. And we're done, right? Then at the end, we can here return an empty array if we've never hit this return statement in the double for loop. So that is the first way of solving this problem, and that's going to run in O of n squared time and O of 1 space, because we're not using a hash table, we're not using any other kinds of arrays or anything. All we're doing is storing 2 extra variables, which we don't even need to do here. It's just for readability purposes. And then at the end, we're returning either an empty array or an array of 2 values. All right, now the way that we really covered in the conceptual overview, which uses the hash table, this is going to be a bit different. So 2-number sum array target sum has the same 2 parameters. Let's comment this first one out. So this one, we're going to start by initializing our hash table. Let's call it, we're going to use just a dictionary here in Python or a JavaScript object. And we're just going to call it nums, short for numbers. And then we're going to start iterating through our array. So we're going to say for num in array, if target sum minus num is in our numbers hash table. Now, what is target sum minus num? That's y, right? That's the value in the conceptual overview that we called y. This is basically our equation, y equals target sum minus x. That was the equation that we covered in the conceptual overview. So if target sum minus num, which is the y value, is present in our nums hash table, well then just return target sum minus num, comma, num. Okay? Otherwise, nums of num is going to be equal to true. Otherwise, we just store our current number in the hash table, and we can just store it as true or whatever you want to put here. Right? I think true makes the most sense here. And then at the end, if we never hit this return statement, then we're just going to return the empty array. And so here, by the way, it might be for readability purposes, it might be better to declare, potential match equals target sum minus num. And then here we can kind of replace target sum minus num with potential match. And we're done. This is going to run in O of n time, not n squared time, but it will also run in O of n space because we're storing these values in the hash table. So I hope this video was helpful. I hope it taught you how to solve this algorithm, and really I hope it showed you how you can use hash table to your advantage. Oftentimes hash tables will make your algorithm use up a bit more space, but run faster and more efficiently. And they're oftentimes going to be worth using, especially in more complicated algorithms that might use up space no matter what, in which case using an additional hash table won't really matter from a space point of view, but will actually help you from a time point of view. All right, that's it for this video. I'll see you in the next one. All right, so the video is not over yet. We still have this third solution that I mentioned earlier in the conceptual overview to implement in code. So let's comment this one out, and let's go over this third solution. So it's going to take the same arguments, right? But at the very beginning, what we're going to do is we're going to sort the array. So we're going to just use, our built-in Python sorting function, and assume, or hope rather, that it uses an optimal sorting algorithm like quicksort or merge sort, and runs in O then log n time, where n is the length of the array. And so then we can initialize our left pointer to be equal to 0, the first value in the array, and our right pointer to be equal to the final value in the array, or the final index in the array, len of array minus 1. So then we can have a while loop, and we can say while left is less than right. So while the two pointers don't overlap, right? Or while they're, one of them is not, while the left one is not past the right one, the current sum is going to be equal to array of left plus array of right. And if the current sum is equal to, whoops, we don't need parentheses here. If the current sum is equal to the target sum, then we can just return left, and or rather array of left and array of right, the two numbers that we have. Then we can say elif, and here let me make a bit of space. Elif current sum is less than the target sum. If our current sum is less than the target sum, then we want to increase the left pointer. So we can say left plus equal to 1. And then elif the current sum is greater than target sum, right plus equal, or right, sorry, minus equal to 1. Because then we want to move the right pointer to the left by 1 position. And that's it. Otherwise, we can just return the empty array. If we get out of this while loop without having hit this if statement here on line 28, and without having returned, two numbers, then that means that we didn't have two numbers that summed up to the actual sum, the target sum, and we return the empty array. So this algorithm is going to run in O of n log n time, and it's going to run in constant space. So you can kind of see that the space complexity here is as good as the first algorithm with the double for loops, better than the one with the hash table. And the time complexity is better, definitely better than the one with the double for loops, but a bit worse than the one with the hash table. And so here, if you were in an interview and you came up with all three of these solutions, you'd be doing really well. You could talk with your interviewer about the trade-offs. Maybe you value space more than time, in which case you'd use this last solution. Otherwise, you'd use probably the solution with the hash table if you valued time the most. So I hope this video was informative for the second time around, and I'll see you in the next one.